Welcome to the intricate, complex world of railway construction. A world where thousands upon thousands of dedicated workers, engineers, and technicians come together with massive machinery, sophisticated technology, and meticulous planning to build the infrastructure that connects nations and changes landscapes forever. Today, we will take you on an extended journey through an entire railway construction project, from its very beginning to its grand completion and opening. This is not a quick process. This is a laborious, methodical undertaking that requires precision at every single step. Watch as mountains are conquered with cutting-edge boring technology. Watch as deep valleys are bridged with enormous steel structures spanning impossible distances. Watch as steel rails are laid with laser precision across hundreds of kilometers. Witness the installation of sophisticated electrical systems delivering power to trains that will carry millions of passengers over decades. This is railway construction at its finest. This is human ingenuity, engineering excellence, and unwavering commitment to building the infrastructure that modern society depends upon. The process is complex, detailed, and utterly fascinating. So settle in, relax, and prepare to observe one of humanity's greatest engineering achievements unfold before your eyes, step by meticulous step. Before even a single piece of earth is moved, before any machinery arrives on site, before the first worker sets foot on the route, an entirely different team arrives with their own specialized equipment and extraordinary responsibility. These are the surveyors, the eyes and minds of the entire project. The surveying process begins with the selection and preparation of the survey area. Teams of surveyors, typically consisting of experienced professionals, arrive at the proposed railway route equipped with sophisticated instruments that represent decades of technological advancement. They carry with them theodolites, remarkable instruments that use optical technology to measure angles with precision measured in seconds of arc. They bring laser measuring devices capable of determining distances across valleys and between peaks with accuracy measured in centimeters, even when those measurements span several kilometers. The surveyors begin their meticulous work at established survey benchmarks, fixed points of known elevation and position. From these reference points, they methodically move forward, taking measurements in every direction. Each surveyor works with intense focus, positioning their instruments with deliberate care, checking and rechecking measurements. The process is slow, methodical, and absolutely critical to everything that follows. Watch as the surveyor positions the theodolite on its tripod, adjusting the legs with careful precision until the instrument sits perfectly level. The surveyor looks through the eyepiece, focusing on a distant reference point held by another team member. They adjust the vertical and horizontal screws with painstaking slowness, fine-tuning the angle until the crosshairs align perfectly. Then comes the reading, a careful notation of the angle measurement, recorded by hand into a field notebook with deliberate script. Beside this traditional work, modern surveying employs GPS satellite technology. Surveyors hold specialized receivers that communicate with satellites orbiting Earth thousands of kilometers overhead. The signal locks, processing, and suddenly the exact position is known, latitude, longitude, and elevation accurate to within a few centimeters. The data flows into portable computers, adding to the growing digital map of the terrain. The surveying teams advance slowly along the proposed route, hour by hour, day by day. They measure horizontal distances using laser rangefinders, where a beam of light travels to a distant reflector and bounces back, the time measured to calculate exact distance. The process is remarkably fast, a measurement obtained in seconds, yet the precision is phenomenal. As the surveyors progress, they place reflective markers at regular intervals along the route. These markers, simple materials with reflective surfaces, serve as reference points for future work. The markers dot the landscape like breadcrumbs, creating a visible line where the railway will soon exist. Some markers are placed on rocky outcrops, others in open fields. Each placement is deliberate and documented. The terrain analysis is relentless and comprehensive. Mountains must be analyzed in detail to determine the optimal tunnel placement. Where should the tunnel go? Should it go straight through or should it curve to minimize the distance? The calculations are complex, involving not just horizontal distance but elevation change, geological composition, and engineering constraints. Every option is considered. Every measurement contributes to the final decision. Rivers and valleys are measured with equal attention. Bridge designers need to know the exact width of the river, the depth of the water, the composition of the riverbed, and the elevation difference between the two banks. The surveyors collect all of this information with painstaking accuracy. They wade into rivers, marking points on banks, taking measurements from multiple angles. The elevation data becomes the foundation for the track gradient calculations. Trains have limits to how steep an incline they can climb. Too steep and the locomotive cannot pull the load. Too shallow and the railway becomes unnecessarily long and expensive. The surveyors measure elevation at intervals of perhaps 50 meters along the entire route, creating a profile that engineers will use to plan the track's vertical alignment. Weather matters little to the surveying teams. They work in rain and the measurements must continue. They work in heat and the instruments must maintain their precision. They work in wind, protecting their sensitive equipment. The work cannot be rushed. Mistakes at this stage would cascade through the entire project, creating problems downstream that would be expensive and time-consuming to correct. Week after week, the survey lines advance. The data accumulates. Measurements pile upon measurements. Each reading becomes part of the growing digital model of the terrain. The landscape, in its full three-dimensional complexity, is gradually captured in digital form. A perfect representation of the mountains, valleys, rivers, and flat plains that the railway must navigate. Teams of engineers process this data in offices far from the construction site. They input the survey information into sophisticated computer models. They draw cross-sections showing elevation profiles. They calculate the optimal alignment that minimizes excavation while remaining practical for train operations. They consider geology, environmental impact, and cost. The decisions made in these offices, informed by the surveyor's precise measurements, will shape every aspect of the construction to come. The surveying phase concludes with the establishment of permanent reference points along the entire route, highly accurate positions that will guide all future construction activities. The surveyors drive tall poles into the ground, marking these positions with paint and flags. They create survey maps showing every measurement, every calculation, every reference point. These maps become the blueprint from which all future work will be conducted. The surveying is complete. The plans are finalized. The engineers have determined the optimal route. Now comes the physical transformation of the landscape. Heavy machinery arrives like an invading army of mechanical creatures. The land clearing and earthwork phase begins. Dozers arrive first. Massive bulldozers with enormous blades capable of pushing entire hillsides. These machines weigh hundreds of tons. Their diesel engines rumble with tremendous power. The operators, sitting in comfortable cabs high above the ground, begin their work with methodical precision. They move forward slowly, the blade dropping into the earth with a grinding sound, and push. The vegetation falls before the advancing blade. Trees that have stood for decades topple in seconds. Undergrowth is scraped away. Topsoil is removed and piled for later use in restoration work. The blade travels back and forth, gradually clearing the route. The operator makes passes, each one slightly offset from the previous, creating a clear corridor where the railway will exist. The rhythm is repetitive and hypnotic. Advance, lower blade, push, raise blade, back up, advance again. Excavators join the bulldozers. These remarkable machines sit on tracks, with long articulated arms ending in buckets capable of scooping several cubic meters of earth in a single motion. The operator moves the control levers with fluid precision. The arm extends, the bucket rotates, the bucket fills with earth and rock, and with a smooth motion the arm retracts and rotates, dumping the load into waiting trucks. Watch the excavator operators focus. They sit in the cab looking at the work area. Their hands move constantly on the levers, making minute adjustments. They position the bucket precisely into the excavation zone, moving with mechanical grace. The bucket fills. You can see the material loading into the bucket, becoming heavier, the hydraulic pressure building. Then comes the moment of extraction. The arm lifting against the weight, hydraulic pressure at maximum, and the material rises into the air. The trucks arrive constantly to remove the excavated material. These are not small trucks. These are massive vehicles, capable of carrying 20 to 30 tons of material. They back into position beside the excavator. The bucket rotates and opens, and tons of earth pour into the truck bed with a thunderous sound. The truck sits lower on its suspension as the weight loads. Then the truck moves forward, the driver coordinating with the excavator operator via radio. Another truck immediately takes its place. The excavation deepens. Where there was hillside, there is now a trench. The walls of the trench become increasingly visible, showing layers of earth and rock, dark topsoil on top, sandy or clayey earth beneath, and eventually bedrock. The excavator continues working, removing all material down to the proper depth for the railway foundation. The process continues for hours, then days, then weeks. Grading equipment arrives for the precision work. These laser-guided graders are marvels of engineering, capable of creating perfectly level or precisely angled surfaces. The operator sits in a comfortable cab, watching a digital display showing elevation data in real time. The grader blade extends beneath the machine. The operator makes adjustments, moving the blade up, down, left, or right based on the elevation information displayed. The grader moves slowly across the cleared area, its blade scraping the earth to the exact elevation required. The display shows in real time whether the grade is high or low. The operator makes tiny adjustments with the control levers. The blade rises slightly, removing more material. The grade improves. The operator continues forward, creating a surface that slopes at exactly the calculated angle, perhaps at a 1.5% grade to allow trains to climb. The finished grade is smooth with no high or low spots. Back and forth the grader moves, making multiple passes. Each pass refines the surface. The earth becomes increasingly uniform and properly aligned. The slope is checked with survey instruments. Laser levels and surveying equipment verify that the grade meets specifications to within a few centimeters across the entire width of the roadbed. Water management is critical during this phase. Soil must be at the proper moisture content to compact properly. Water trucks arrive and spray the freshly graded earth. The water soaks into the soil, moistening it uniformly. The application rate must be controlled. Too much water and the soil becomes muddy and won't compact. Too little and it remains too dry. The water truck operators have years of experience, and they apply water with judgment and experience. Vibratory compaction equipment moves across the moistened soil. These machines, ranging from small walk-behind vibratory plates for confined areas to enormous self-propelled compactors for large areas, compress the earth with thousands of vibrations per minute. The vibration liquefies the soil particles momentarily, allowing them to settle into a denser configuration. Layer after layer is created, each layer compacted individually before the next layer is added. Watch the compaction process in detail. The vibratory compactor moves forward slowly, its base plate vibrating at high frequency. You can see the earth under the plate compacting and settling. The machine travels forward at maybe 5 kilometers per hour, very slow, very deliberate. It reaches the end of its pass, stops, turns, and makes another pass adjacent to the first. The controlled overlap between passes ensures complete compaction. The densification continues for days. Material is added on top in lifts, perhaps 30-centimeter layers. Each layer is compacted until it reaches the required density specification. Testing equipment, small devices that measure soil density, is used at intervals to verify that the proper compaction has been achieved. The work is methodical, repetitive, and absolutely critical to the railway's long-term stability. Trucks continue to remove unsuitable material and bring in additional fill material as needed. The material flows in a constant stream, excavators loading, trucks carrying, dumpers unloading at designated sites. The logistics are complex, coordinated by dispatch teams who track each truck, directing them to the appropriate location. The system must work smoothly or the entire operation backs up. Environmental controls are put in place. Dust suppression is critical. Water trucks spray the work areas regularly to prevent dust from becoming airborne. Erosion control measures are installed to prevent stormwater from carrying sediment off-site. Sediment barriers and settling ponds capture material before water leaves the work area. The earthwork phase continues relentlessly, day after day. The landscape is gradually transformed from its natural state into an engineered roadbed suitable for railway construction. The work is never glamorous, yet it is absolutely essential. Without proper earthwork, every phase that follows would be undermined. The foundation must be solid, level, and properly compacted. When this phase is complete, the corridor is ready for the next transformation. A mountain stands in the way. The route will go through it, not around it. The tunnel must be excavated, a process that combines engineering marvel with sheer determination and considerable danger. Tunnel boring equipment is positioned at the tunnel entrance. This is not simple excavation equipment. This is a tunnel boring machine, a TBM, a technological wonder that represents the pinnacle of tunneling achievement. The machine is enormous, stretching perhaps several hundred meters from the cutting head at the front to the support equipment at the rear. The front of the TBM is dominated by the cutting head, a massive circular structure with numerous cutting tools embedded around its face. These cutting tools are made of hardened steel and carbide, capable of breaking apart even very hard rock. The cutting head rotates continuously, driven by powerful hydraulic motors. As it rotates, the cutting tools attack the rock, breaking it apart into manageable pieces. Watch as the cutting head slowly presses into the rock face. The sound is tremendous, a deep grinding sound as the tools scrape and pound against stone. Rock fragments and dust are created by the millions. Behind the cutting head, a conveyor system captures the broken rock and carries it backward to collection points where it is loaded into trucks for removal. The system must work smoothly. If rock accumulates faster than it can be removed, the machine stalls. The TBM advances slowly into the mountain. Advance rates vary depending on rock conditions, but perhaps 2 to 3 meters per day is typical. The pace seems glacial compared to surface work, but it is actually quite good for underground work. The machine presses forward relentlessly, eating through stone. Behind the cutting head, the tunnel structure is immediately installed. As the TBM advances, support equipment places tunnel lining, usually concrete segments assembled together to form a ring. These segments are positioned behind the cutting head, held temporarily by hydraulic jacks. The jacks push the entire TBM forward using these newly placed ring segments as reaction points. The old rings slide backward as new material is installed, and the jacks grip the new rings, pushing the machine forward another meter. The process is continuous and coordinated. Advance, install lining, advance, install lining. The tunneling crew manages this process with considerable skill, monitoring machine parameters constantly. Pressure within the cutting chamber must be maintained at precisely the right level to support the tunnel heading. Too much pressure and the ground is over-excavated. Too little and the tunnel face can collapse. Experienced operators maintain this balance throughout. Ventilation is critical. The tunneling environment is confined and potentially deadly. Ventilation pipes run the entire length of the tunnel under construction. delivering fresh air to the working area and removing exhaust gases and dust. Powerful fans push tens of thousands of cubic meters of air through these pipes every hour. Workers wear safety equipment and respiratory protection. They work in shifts in the harsh underground environment, knowing they are part of something momentous. The TBM encounters different rock conditions. Some areas are soft and easily broken, others are extremely hard. When hard rock is encountered, the pace slows. Operators make adjustments to the machine's parameters, increasing pressure or changing cutting tool positions. When soft rock is encountered, the risk is different, the risk of collapse. Support pressure must be maintained carefully to prevent the tunnel heading from collapsing. Every 100 meters or so, the tunnel is checked for survey accuracy. Specialized instruments measure the tunnel position and alignment. Data is collected and analyzed to ensure the tunnel is advancing along the planned centerline. Small corrections can be made by the TBM operators, adjusting the cutting head position slightly to bring the alignment back to design specifications. Over several hundred meters, these small corrections accumulate and ensure the tunnel reaches its destination on the correct line. After the TBM has advanced some distance, perhaps several hundred meters, the tunnel undergoes a secondary reinforcement process. The concrete segments installed by the TBM are the primary support, but additional reinforcement is often added. Steel mesh may be installed and additional concrete sprayed on the tunnel walls to add another layer of protection and stability. This secondary support work follows behind the TBM, gradually hardening and strengthening the tunnel structure. Ventilation system installation follows. Large ventilation pipes are suspended in the tunnel, delivering fresh air to the heading. Exhaust air return paths are established. Lighting is installed in the completed sections. Electrical systems are run through the tunnel to power equipment and lighting. The tunnel gradually becomes a functioning structure, not just a hole in the ground. The tunneling effort continues without stopping. Shifts change at regularly scheduled intervals and fresh crews take over the work. The TBM continues advancing day and night. The sound of grinding rock becomes a constant in the mountain's depths. The rock face gradually advances, 1 meter at a time, day after day, week after week. Months pass. The TBM advances kilometers through the mountain. The work is tireless, relentless, and in its own way quite beautiful. The precision required, the engineering ingenuity, the coordination of dozens of workers and complex machinery, it all comes together to accomplish what seemed impossible. Drilling through a mountain to create a tunnel for trains. Eventually, perhaps after many months of continuous work, the TBM approaches the exit portal on the far side of the mountain. The final meters of rock are broken away. The cutting head emerges from the mountain into open air on the far side. The tunnel is through. The mountain has been conquered, but the work is not yet finished. The tunnel must be fully reinforced, ventilation systems completed, lighting installed throughout, and all safety systems verified. Crews work in the completed tunnel, making final inspections, ensuring every segment is properly seated, checking alignment one final time. The tunnel gradually transitions from an active excavation project to a permanent structure. Dark, cool, and strong, built to last for centuries. The river cannot be bridged by building through it. Instead, a bridge must span across it, an elegant structure that will carry trains high above the water, connecting the two sides of the valley. Bridge construction is a complex engineering undertaking in itself. First comes the foundation work. The bridge must rest on supports capable of holding the enormous weight of trains traveling across its length. These supports must be placed on solid ground, which may be beneath the riverbed or on the riverbanks. For deep rivers, the challenge is significant. Pile driving equipment arrives at the site. This is massive machinery, a crane-mounted hammer suspended high in the air. The hammer consists of a heavy weight, perhaps dozens of tons of steel, that is lifted high using the crane and then dropped repeatedly onto a steel pile below. Each impact drives the pile deeper into the riverbed. Watch as the pile driving begins. The operator controls the crane, raising the hammer high, lifting it perhaps 10 meters. Then the hammer is released. It falls freely, accelerating under gravity. At the moment of impact, it strikes the top of the steel pile with tremendous force. The pile shudders from the impact and settles deeper into the ground. The sound of impact carries far, a deep boom that echoes around the work site. Immediately, the hammer is lifted again. Raised high, released, falling, impacting, settling, the cycle repeats. Over and over, hour after hour, the pile is driven deeper into the earth. The operator watches carefully, managing the hammer height and release timing to maintain proper striking sequence. The pace can be rapid, perhaps 10 to 20 blows per minute, but the process is unrelenting. Deep below, the pile penetrates further and further into the riverbed. The pile eventually reaches refusal, a point where it cannot be driven deeper because it has reached bedrock or soil conditions that cannot be compressed further. This is the target depth, verified with measurements and calculations. The pile has been driven to the required depth for the bridge foundation. Multiple piles are driven in sequence, creating an array of pilings that will support the bridge structure. Each pile is driven to similar depths, creating a level platform upon which the bridge will rest. The driving process continues for days or weeks, depending on how many piles are required and how deep the riverbed is. Once piles are in place, caissons are positioned and concrete is poured to create the bridge piers, the towers that will support the bridge structure. These piers must be massive to support the weight they will carry. Concrete is delivered continuously by truck, poured into formwork that shapes the pier. The concrete fills the form layer by layer and begins to cure. Watch the concrete pour in detail. Trucks arrive, backing carefully into position. A chute extends from the truck's mixer drum to the formwork. The concrete flows, a steady stream of gray material, still wet and plastic. The material fills the form, flowing into corners and around steel reinforcement embedded in the concrete. Workers use tools to remove air bubbles, ensuring the concrete fully consolidates. The pour continues hour after hour until the pier form is completely filled. The concrete hardens. Days are required for it to reach sufficient strength to support the next phase of construction. During this time, weather must be monitored. Rain could damage the concrete. Freezing temperatures could cause damage if the concrete is not properly protected. But gradually, the concrete hardens and strengthens, becoming the solid foundation that will support the bridge. Once the piers are sufficiently cured and strengthened, the structural steel begins to arrive. Enormous I-beams and box sections, the main girders that will span the river, are transported to the site on specialized trucks. These beams are incredibly large and heavy, sometimes weighing hundreds of tons each. Cranes position the beams over the gap between piers. The lifting operation is carefully coordinated. The crane operator controls the boom, hoisting the beam high into the air. Ground personnel guide the beam using lines, positioning it precisely over the gap. The beam is lowered slowly, very slowly, guided into its final position. Temporary supports hold it in alignment. As beams are positioned, other workers move into position with bolting equipment. The connections between beams and to the piers must be made with hundreds or thousands of bolts, depending on the bridge size. Power tools, pneumatic nut runners, are used to tighten the bolts, drawing them to precise tension specifications. The work proceeds methodically, bolt by bolt, connection by connection, building the bridge framework. Welding follows bolting in some locations. Where beams connect to each other, permanent welds create integrated structure. Welders move into position with their equipment. The welding arcs ignite with brilliant white light. Metal flows as the welder carefully moves the torch along the joint, fusing the metal together. The work requires skill and focus. A good weld is strong and will last for decades. A poor weld is a structural liability. The welded joints are then inspected. Ultrasonic testing and visual inspection verify that the welds are of sufficient quality and free from defects. Testing is rigorous because weld quality directly impacts bridge safety. As the structural steel is completed, the deck is installed. This is typically a reinforced concrete slab cast over the steel beams. Formwork is positioned, reinforcing steel is installed, and concrete is poured, creating a solid surface. The concrete must be level and smooth, with proper drainage to shed water away from the structure. Railings are installed along the edges of the deck for safety. These are substantial steel or concrete structures capable of stopping a train if necessary. The railings are positioned at specific heights determined by railway safety standards. As the bridge nears completion, finishing touches are added. Waterproofing membranes protect the concrete from water infiltration and damage. Drainage systems are installed to manage water. Expansion joints are positioned to allow the bridge to expand and contract with temperature changes. Lightning protection is installed to safely conduct lightning strikes to ground. The completed bridge is beautiful and functional, an elegant structure spanning the river, supported by its piers, ready to carry trains across the valley that once seemed to bar the railway's path. The bridge stands as a testament to engineering achievement, a permanent monument to human determination and capability. The earthwork is complete. The tunnels are finished. The bridges span the gaps. Now comes the foundation upon which the rails will rest. The ballast and sleeper installation phase is critical to railway stability and longevity. Ballast is the foundation, millions of tons of crushed stone of specific size and quality. This material provides the foundation for the sleepers and distributes the weight of trains across a wide area, preventing the railway from settling unevenly. The ballast must be of a consistent size, typically between 25 and 50 millimeters, and must be of a suitable rock type, usually granite or similar hard rock that resists breakdown. Dump trucks arrive with ballast material. They back into position along the track bed and dump their loads. The ballast tumbles out, creating piles along the route. The material spreads across the ground, and gradually the ballast material extends for the length of the railway route. Specialized machinery spreads and levels the ballast. These machines have spreading equipment that distributes the material evenly across the track bed, creating a uniform layer. The material is spread in a consistent layer, typically perhaps 30 centimeters deep, prepared to receive the sleepers. Vibratory compaction equipment moves across the ballast layer, vibrating and settling the stone particles. The vibration helps the individual stones nestle together, creating a solid, stable foundation. The stone shifts and settles under the vibration, the particles compress together, and gradually the loose pile becomes a cohesive, stable layer. Watch this process in detail. The vibrating compactor moves slowly forward, its base plate shaking at high frequency. The stone beneath visibly settles and compacts. The compactor moves in straight lines along the track bed, making multiple passes to ensure complete compaction. The rhythm is repetitive and hypnotic, back and forth, gradually transforming loose material into solid foundation. The compacted ballast extends the full length of the railway. Millions of tons of stone now form the foundation layer. The work continues for weeks or months, depending on the railway length, but the process is consistent and methodical throughout. Once the ballast is properly compacted, the next critical component is installed: the sleepers. Sleepers, also called railway ties or cross ties, are the cross members that support the rails and distribute the train's weight across the ballast. Modern sleepers are typically made of reinforced concrete, though wooden sleepers are still used in some locations. These are large, heavy beams, typically weighing several tons each. Sleepers are positioned on the compacted ballast at precise intervals, typically approximately 60 centimeters apart for modern railways. The spacing is critical. If sleepers are too far apart, the rail will not be adequately supported and may flex excessively under train weight. If too close together, cost and weight increase unnecessarily. The spacing must be consistent the entire length of the railway. Specialized machinery positions the sleepers. These machines move along the track bed, mechanically lifting and placing sleepers at the correct spacing. Crews follow behind, verifying that each sleeper is properly seated in the ballast and is level from side to side. Watch the sleeper placement process. The specialized placement machine positions a sleeper and lowers it onto the ballast. Workers inspect the placement, checking with leveling instruments to ensure the sleeper is properly aligned and level. If adjustment is needed, the sleeper is repositioned by manual effort or by machine equipment. Once properly positioned, the sleeper is considered in place. The sleepers are placed in long lines extending down the track. Each sleeper is individually positioned and verified. The workers move methodically along the line, checking alignment, adjusting sleeper position as needed, ensuring consistency. The process is slow and careful. Typically, workers might place only a few hundred sleepers per day. But the work must be precise. As sleepers are placed, additional ballast material is packed around them. This ballast holds the sleepers in position and provides the foundation they rest upon. Material is hand-worked around each sleeper, and vibratory compactors make additional passes to ensure the ballast is fully compacted around the sleepers. The completed sleeper installation presents a striking visual. Long lines of concrete sleepers extending toward the horizon, evenly spaced, creating a visual rhythm. The sleepers sit upon the ballast foundation, ready to support the rails that will soon rest upon them. Quality control is maintained throughout. Measurements are taken periodically to verify sleeper spacing is correct. Elevations are checked to ensure sleepers are at the proper height. Surface inspection verifies that sleepers are properly seated and aligned. Any deviations from specification are corrected immediately. The sleeper installation continues the full length of the railway. Where the railway crosses special features, bridges, tunnels, switches, and crossings, the sleeper pattern may be modified to meet specific requirements. But the overall pattern and spacing remains consistent. When this phase is complete, the foundation is truly ready, a solid, stable platform upon which the rails will rest. The moment approaches that defines the railway project, the laying of steel rails. These long bars of precisely manufactured steel will carry the weight of trains, hold them on the correct path, and define the railway for decades. Rail laying is a complex, coordinated process requiring precision and timing. Rails are manufactured off-site in specialized mills. The steel is formed, rolled, cooled, and finished to precise specifications. Rails must be straight to millimeter tolerances, their surfaces smooth, their strength consistent. Modern rails are often in very long lengths, sometimes several hundred meters, rather than the shorter rails of earlier eras. These long rail sections simplify the track and reduce the number of joints. Rail sections arrive at the track site by rail or truck. Long trains of rail cars may be spotted along the route, carrying the rail that will eventually form the permanent track. The rails must be organized and prepared before installation, positioned so they can be accessed by the rail laying machines. Rail laying machinery is specialized equipment, typically a train of specialized cars that collectively form a rail laying system. The front of the system includes a lifting mechanism that picks up rail sections and positions them on the sleepers. Behind this are cars carrying material needed for the installation: fasteners, lubricant, and support equipment. Watch as the rail laying train approaches a section of installed sleepers. The train stops. Workers position rails in front of the laying machine. The machine's lifting mechanism engages, picking up a rail section and positioning it above the sleepers. Hydraulic systems lower the rail gradually, positioning it on the sleepers. Once the rail is positioned, alignment and leveling become critical. The rail must sit on the sleepers at the proper height, the same height as the rail that preceded it, ensuring a continuous level surface. The rail must be positioned with its inner edge at the proper gauge. The distance between the two rails is critical. Standard gauge is 1,435 millimeters. Even small deviations would cause train problems. Surveying equipment verifies the rail position. Laser levels and optical instruments check the rail height. Gauge measuring tools verify the distance between rails. If adjustment is needed, workers make small modifications, repositioning the rail until it meets specification. Once the rail position is verified as correct, the fastening process begins. Fasteners, clips and bolts that secure the rail to the sleepers must be installed along the entire length of the rail. Power tools, pneumatic tools with impressive speed and power, tighten the fasteners. The sound of the tools is rapid and rhythmic. Click, 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 click as fasteners are driven and tightened. Watch the fastening crews work. They move along the rail in coordinated teams, each worker responsible for specific fasteners. One worker positions a fastener, another tightens it with the power tool, a third verifies that proper tension has been achieved. The work proceeds rapidly, dozens or hundreds of fasteners being secured in a few hours. The tightening must be precise. Too little tension and the fastener may loosen under vibration from passing trains. Too much tension and the bolt may break or strip. Torque wrenches ensure that fasteners are tightened to exactly the specified tension. The specification is careful and the quality control is rigorous. After the rail section is fully fastened, the next rail section is positioned. But rail sections must be joined together, end to end, to create a continuous rail. The joint is critical. The two rail ends must meet perfectly with no gap or misalignment. The connection must be strong, capable of transferring the train's weight smoothly from one rail section to the next. Welding creates a permanent rail joint. Specialized rail welding equipment is positioned at the joint. The two rail ends are held in perfect alignment by the equipment. The rail surfaces are cleaned to remove contaminants. Then the welder ignites the welding arc and metal flows, fusing the two rails together. The welding process is different for rail than for other structures. Rail welding typically uses thermite welding, a process where a thermite reaction creates molten metal hotter than any other welding process. The molten metal flows into a mold around the rail joint, fusing the two rails into a single piece. When the metal cools, the two rails are permanently united. Watch this remarkable process. The thermite crucible is positioned above the joint. The thermite reaction ignites. A brilliant white flash of extraordinary brightness, visible even in daylight. Molten metal flows downward into the mold, engulfing the rail ends in liquid metal. The temperature is tremendous. The metal flows like water, filling every gap and creating a perfect union of the two rails. As the metal cools, workers carefully manage the cooling process. Quenching water or air cooling is applied in controlled fashion to prevent cracking or distortion. The joint is then dressed. Excess metal is removed using grinding equipment, creating a smooth rail surface. The joint is inspected using ultrasonic equipment to verify no internal defects were created during welding. The result is a rail joint that is as strong as the parent rail material itself. Modern welded rails can be operated at unlimited speed. There is no speed restriction at the joint. The rail is continuous, permitting smooth, quiet train operation. The rail laying continues along the entire railway length. Rail section after rail section is positioned, fastened, and joined. The process is relentless, methodical, and incredibly important. Weeks or months may be required to lay rail for the entire railway length, but when it is complete, the most visible and important component of the railway is in place. As rails are laid, they are tested and inspected. Track geometry is verified using specialized inspection equipment. The gauge is checked. The distance between rails must be exactly right. The alignment is verified. The track must curve smoothly without sharp kinks. The surface level is checked. The rails must sit at the proper height, providing a smooth surface for the train wheels. The newly laid track is also subjected to a stress relief process. New rail has internal stresses from manufacturing and installation. These internal stresses can cause rail to change shape slightly over time. To prevent problems, the rail is often subjected to controlled stress relief. The rail is heated to specific temperatures, held at those temperatures, and then cooled carefully. This process relieves internal stresses and stabilizes the rail geometry. The rail becomes more stable and predictable in service. Continuous welded rail, CWR, requires even more careful management than jointed rail. CWR extends for kilometers without intermediate rail joints. As temperatures change with the seasons, the rail naturally wants to expand and contract. The track structure must accommodate this thermal movement. On curves and in switches, rail movement is constrained, and the track structure must be strong enough to hold the rail in place despite the thermal stresses. Neutral temperature setting is critical for CWR. The rail is heated to a specific temperature, usually around 32 degrees Celsius, at which it is stressed to a neutral tension. Rail fasteners are tightened to specific specifications at this temperature. As the season changes and the rail grows warmer or colder, it expands or contracts, developing compression or tension stress, but the magnitude never becomes excessive. This careful management prevents rail buckling in summer heat or rail failure in winter cold. The completed rail line stretches across the landscape, shiny new steel reflecting sunlight, perfectly aligned, ready to carry trains at high speed. The precision visible in the new track is remarkable. The rails are parallel to millimeter accuracy for hundreds of kilometers. The track sits on a solid foundation of ballast and sleepers. The joining points are seamlessly welded. This is the product of weeks or months of dedicated work by specialized crews. For electric railways, the overhead catenary system is essential. This is the wiring system that delivers electrical power to the trains as they travel along the route. The catenary system must be installed with precision, as even minor misalignment causes problems with the train's pantograph connection. Steel catenary towers are positioned along the route at regular intervals, typically every 50 to 100 meters depending on design specifications. These towers are tall structures, perhaps 5 to 10 meters above the track, capable of supporting the weight of the catenary wire system and the dynamic forces from the train pantograph. Tower installation begins with foundation work. Each tower position is drilled or excavated, and a foundation is installed, typically a concrete base set into the ground. The tower is positioned on this foundation and secured. Bolts are tightened, ensuring the tower cannot move. The tower stands ready for the wiring installation. The catenary system consists of multiple components. The main catenary wire, a thick, high-strength steel or aluminum alloy wire, runs from tower to tower at a height of about 5 to 6 meters above the track. This is the wire that the train's pantograph slides along, drawing electrical power. The tension in this wire is critical. It must be tight enough to provide support for the pantograph contact, but not so tight that it puts excessive stress on the towers. The catenary wire is carefully positioned between towers. Specialized teams use insulated equipment to handle the wire, preventing any conductive contact. The wire is strung between towers, with the tension being controlled by adjustable equipment at each tower. The tension is set to precise specifications using calibrated tension meters. Watch the tension setting process. The catenary wire is pulled taut between towers using motorized equipment. As tension increases, calibrated meters measure the tension. The tension is adjusted until the reading matches the specification. Only then is the wire locked in place with fastening equipment at each tower. Along with the main catenary wire, dropper wires are suspended downward from the catenary wire. These droppers support a messenger wire that runs parallel to the track. The messenger wire distributes the electrical current from the catenary wire to multiple pantograph contact points, ensuring even wear of the contact surfaces. Insulators are installed at regular intervals along the catenary system. These are ceramic or composite components that electrically isolate different sections of the catenary wire. Electrical substations feed power into the catenary system at specific points, and the insulator sections prevent power from feeding back into sections where it is not intended. The overhead system must be checked for proper height, alignment, and tension. Specialized equipment measures the height of the catenary wire at multiple points along each tower section. The measurement is taken at midspan between towers and at the tower positions themselves. The measurements must fall within tight tolerances, typically within 50 millimeters of the design height. The horizontal alignment is equally important. The catenary wire must be positioned directly above the track centerline. If it is offset to one side, the train's pantograph cannot maintain proper contact. Laser alignment equipment verifies that the wire is correctly positioned. If adjustment is needed, the wire is repositioned by loosening and retensioning the fastening equipment at the towers. Electrical infrastructure must be installed to distribute and control power to the overhead system. Substations are positioned at intervals along the railway, perhaps every 10 to 15 kilometers. These substations convert the incoming utility power into the proper voltage and frequency for the railway system. Inside the substation building, transformers convert the utility voltage to the railway voltage. Rectifier equipment, if DC power is needed, converts AC power to DC. Circuit breakers and protection equipment ensure safe operation. Switchgear allows power to be controlled and distributed to different sections of the catenary. The equipment is complex, highly engineered, and critical to the entire electrical system. All equipment is connected via cables buried or suspended in conduits. These cables carry power and control signals throughout the system. The cables are color-coded and carefully labeled so technicians can identify them and make connections properly. Every cable connection is checked and verified for proper continuity and insulation. Grounding systems are installed to provide a safe path for stray electrical current. Every substation and major structure is grounded with copper rods driven into the earth or with ground plates buried in the soil. These grounding systems ensure that if electrical faults occur, the current is safely conducted to ground rather than through workers or equipment. The overhead system and electrical infrastructure must work together seamlessly. The catenary system is supplied with power from the substations. The electrical current flows through the overhead wire, and the train pantograph collects this current and delivers it to the train's traction motors. The returning current flows through the rail back to the electrical substations, completing the circuit. Extraordinary precision is required for this electrical system to function properly. Voltage must be maintained within narrow tolerances. Current distribution must be balanced across multiple feeding points. Protection systems must respond instantly if faults occur. Testing and verification is extensive and rigorous. Modern railways depend on sophisticated signaling systems to manage train movements safely. These systems guide trains, communicate operational requirements to drivers, and prevent dangerous situations like trains operating too close together or entering occupied sections. Signal structures are positioned along the railway at designated locations, typically at regular intervals and at important locations like level crossings, switches, and junction points. These structures mount the actual signal devices, lights or mechanical indicators that communicate information to train drivers. Three-aspect signals are the most common. These signals display three different indications: red, stop; yellow, caution/prepare to stop; and green, proceed. The signal aspects change to display the proper indication based on conditions on the track ahead. Watch as a signal structure is installed. The mounting poles are driven or set into position alongside the track. The signal head, the framework that holds the individual signal lights, is positioned at the proper height and angle. The signal aspect indicators are mounted in the signal head at positions visible to train drivers. Wiring is run from the signal head down to the signal control equipment. Each signal is controlled by electronic logic devices that determine what indication should be displayed. The logic is determined by occupancy sensors, devices that detect whether a track section is occupied by a train or is empty. If a section is occupied, the signal behind it must display red, stop. If the section ahead of the occupancy is also clear, the signal behind it might display yellow or green, indicating the approaching train can proceed. Occupancy detection employs several methods. Track circuits measure electrical conductivity through the rails. A current flows through a rail section through a relay. If a train is present, its wheels short the circuit and the relay de-energizes, indicating occupancy. Modern systems might use axle counters, equipment that counts the number of train axles entering a section and compares to those exiting, indicating whether the section is occupied. Level crossings, where roads cross the railway, require special safety protection. Sensors detect approaching trains at significant distance before the crossing. When a train is detected as approaching, automated equipment is triggered. Crossing gates begin to lower, lights begin to flash, and bells or horns begin to sound, warning vehicle drivers that a train is approaching. Watch the level crossing activation. Sensors detect a train at perhaps 1 kilometer distance. Electrical signals are transmitted to the crossing protection equipment. The crossing gates, initially raised up to permit vehicle traffic, begin to lower under motorized control. The lights begin flashing, red lights alternating on and off. The warning bell or horn sounds at high volume. Vehicle drivers seeing and hearing these warnings stop their vehicles and wait until the train passes. Once the train has completely passed the crossing and sensors detect the track is clear, the gates raise, the lights stop flashing, and the warning sounds cease. Switch machines control track switches, locations where the railway splits into multiple directions. The switch machines move the movable rails to position them toward one direction or another. The correct position of the switch is critical. If a train enters a switch in the wrong position, it could derail catastrophically. Modern switch machines are electrically powered and electrically monitored. Before a train is permitted to enter a switch, the switch position is set, and then the system verifies that the switch is in the correct position. Only after verification is the signal cleared to permit the train to pass. If the switch is not in the proper position or if the position cannot be verified, the signal remains red and the train cannot proceed. Switch detection ensures that if a switch moves unexpectedly while a train is traversing it, this condition is immediately detected and action is taken to prevent catastrophe. If a switch is found to be in the wrong position at the moment a train is expected to use it, alarms sound and operators are alerted. The signaling system includes backup systems and safety interlocks. These are designed so that no single failure can cause an unsafe condition. If a signal fails to display properly, backup equipment ensures the train is protected. If a switch motor fails, mechanical systems ensure the switch cannot be in an ambiguous position. Central control facilities monitor the entire railway signaling system. Operators in these facilities have visibility into the state of the entire railway, where trains are located, signal statuses, switch positions, level crossing activations, and many other parameters. The operators can remotely control switches, adjust signal operation, and coordinate train movement across the system. The signaling system is tested extensively before operation. Every signal is tested to ensure it displays properly. Every switch machine is tested to ensure reliable operation. Every level crossing is tested to ensure all protection systems function. Occupancy detection equipment is tested to ensure accurate detection. The integration of all systems is tested to ensure they work together properly. Stations are the interfaces between the railway and the communities it serves. Passengers board and alight at stations. Freight is loaded and unloaded. Maintenance and storage facilities serve the trains. Stations must be functional, safe, and often architecturally significant. Station construction begins with site preparation and foundation work. The station location is typically situated where the track will pass through the property. Foundations are excavated and prepared. Reinforcing steel is positioned in the excavation. Concrete is poured, creating the structural foundation for the station building. The station building structure is erected. Concrete or structural steel provides the main structural system. Concrete columns rise from the foundation. Steel beams span between the columns, creating the framework. The framework is designed to create large open spaces within the station, allowing passenger movement flow. The main booking hall is usually the largest and most public space in the station. This is where passengers buy tickets, plan their travel, and move toward the platforms. The booking hall must accommodate large numbers of people during busy periods. The space is designed with high ceilings and clear sight lines. Ticketing counters are positioned around the perimeter. Information displays show train schedules and other travel information. Watch the ticketing counter installation. The counters are positioned at intervals in the booking hall. Each counter is equipped with a cash drawer, computer terminal, and communication system. The counters are installed at a standard height suitable for both seated and standing ticket agents. The design is practical and functional, facilitating the transaction of thousands of tickets daily. Waiting areas are provided for passengers waiting for their trains. Comfortable seating is installed, benches or individual seats. The furniture is selected to be durable and easy to maintain. The waiting areas are positioned with views toward the platform areas, allowing passengers to see their train when it arrives. Restrooms are essential facilities in any station. These are installed in convenient locations accessible to all passengers. Multiple stalls are provided to serve the large number of passengers using the station daily. Facilities are designed for hygiene and maintenance. Water fountains provide drinking water. The platform is the critical area where passengers board and alight from trains. The platform must be large enough to safely accommodate the number of passengers expected during peak hours. The platform surface is constructed of durable material capable of withstanding heavy foot traffic. The platform edge is finished with distinctive marking. Yellow lines indicate where the platform ends and the tracks begin. The platform must be at the exact correct height to align with the train doors. Typically, this is around 1 meter above the track. The platform must be level. Any slope would make it difficult to board or alight. The platform is finished with proper drainage to shed water and prevent water accumulation. Platform shelters provide protection from rain and sun. These are typically simple structures, a steel frame with a roof panel. The shelters are positioned to provide coverage for waiting passengers while not interfering with train operations. Transparent panels allow passengers to see approaching trains. Lighting is installed throughout the station to ensure visibility and safety. The booking hall is illuminated with bright lighting to facilitate ticket sales and information gathering. Platforms are illuminated for safe passenger movement and to deter criminal activity. Tunnels and underpasses are illuminated for safety. Electrical systems are distributed throughout the station. Power must be delivered to ticket counters, lighting, communications equipment, and ventilation systems. Backup power systems, generators or batteries, ensure critical systems continue operating even if utility power is lost. Ventilation systems maintain comfortable air quality in the station. Fresh air is drawn in and stale air is exhausted. The system is designed to provide adequate air changes without creating drafts or uncomfortable air movement. In enclosed stations, ventilation is particularly important to prevent accumulation of diesel fumes from trains. Communication systems connect the station to the central control facility and to train operators. Announcement systems allow station staff to communicate with passengers. Radio systems connect to train crew. Telephone systems provide communication for emergency services and other needs. The station building envelope, the roof and walls, must be weathertight and thermally efficient. Rain must not penetrate the building. In cold climates, the building must be heated. In hot climates, the building should be designed for natural ventilation or air conditioning. The building envelope is tested to ensure weather tightness. Exterior finishing includes wall materials, roofing, and any architectural details. The design may include decorative elements that give the station architectural character. Modern stations often feature attractive designs that become local landmarks. Security systems are installed at many stations. Video cameras monitor passenger areas and critical locations. Access control systems may restrict entry to certain areas. Alarm systems alert to emergency conditions. The completed station is a complex facility that serves many functions. It is a transportation hub, a commercial space, a community gathering place, and a symbol of the railway itself. The station design and quality significantly influence passengers' experiences and the public perception of the railway. Before the first revenue service train departs, the entire railway system must be tested exhaustively. Every component must be verified to function correctly and safely. This testing phase is thorough and methodical, sometimes lasting weeks or months. Test trains begin their journeys on the new track. These trains are not revenue passenger or freight trains. They are special test trains used only for this purpose. The test trains carry specialized instrumentation that measures vibration, acceleration, wheel loads, and many other parameters. The instrumentation records data continuously as the train travels, creating a record of how the railway system is performing. The test train starts slowly. The driver operates the train at perhaps 10 kilometers per hour, gradually increasing speed as the route is validated. Speed is increased incrementally, 5 kilometers per hour, 10 kilometers per hour, 20 kilometers per hour, 30 kilometers per hour, each speed step being validated before the next increase. At each speed, the railway is observed and measured. Vibration sensors on the track and on the train measure how much the track deflects and how much the train vibrates. These measurements are compared to expected values. If vibration is excessive, the train stops and the problem is diagnosed. Braking is tested repeatedly. The train accelerates to a certain speed and then applies full brakes. The braking performance is measured. How quickly does the train decelerate? Do the brakes perform equally on all wheels? Does the train stop smoothly or with excessive jerking? The data is recorded and analyzed. Lateral acceleration is measured in curves. As the train navigates a curve, centrifugal force pushes the train outward. The superelevation of the track, banking the curve inward, helps counter this force. The amount of lateral acceleration felt by instruments mounted on the train is measured. Excessive lateral acceleration could indicate a problem with the curve banking or track geometry. Track geometry is measured in detail using specialized equipment. A track geometry measurement car, a specially equipped train car with laser measurement equipment, travels the entire railway route, measuring track alignment, gauge, elevation, and curvature. The data is recorded and compared to design specifications. Any deviations are documented. The overhead electrical system is tested under electrical load. A test train draws power from the overhead catenary system. The voltage at the train is measured. It must be within acceptable limits. The current drawn is measured. The pantograph's contact with the overhead wire is observed to ensure good electrical contact. The electrical system supplying power to the overhead catenary is tested. Substations are verified to be delivering proper voltage and current. Power distribution to various sections of the line is checked. Protection systems are tested to ensure they respond properly to electrical faults. The signaling system is tested exhaustively. Every signal is verified to display the correct aspect. Every signal transition is tested. When train occupancy changes from one section to another, the signal behind the train must change to red, and the signal behind that must change to yellow. The sequence of signal changes is observed and verified. Switch operation is tested repeatedly. Each switch machine is operated many times to ensure reliable function. The electrical verification systems that confirm switch position are tested. The interlocking system that ensures switches are in correct position before allowing trains to enter is tested. Level crossing protection systems are tested at each crossing. The gates are raised and lowered to ensure smooth operation. The lights are verified to illuminate properly. The warning bell or horn is tested. The timing of all elements is verified to ensure proper coordination. Communication systems are tested. The signaling system, the railway control center communications, the passenger announcement system, emergency communications. All must function reliably. The train operating crew is trained and practices extensively. The drivers learn the railway characteristics, the signal system, the station locations, and emergency procedures. Simulators may be used to practice normal and emergency operations before operating actual trains. Safety systems are tested, particularly emergency systems. If an emergency condition is detected, excessive speed on a curve, a derailment, a collision threat, the railway's automatic protection system should respond. These automatic systems are tested to ensure they function properly and protect the train and occupants. Inspection teams walk the entire railway route, checking everything. Track inspection teams check for proper rail alignment and condition. Catenary inspection teams check the overhead system. Bridge inspectors verify bridge conditions. Tunnel inspectors verify tunnel support systems. Every component is checked. Documentation is compiled showing that every system has been tested and verified. Reports are filed with regulatory authorities. Certifications are obtained from inspectors. The railway receives approval to begin revenue operation. Test operations may continue for some time before opening to the public. These operations allow the railway staff to become fully comfortable with the system. Any remaining issues are identified and corrected. The staff becomes proficient in the operation of the complex system. The day arrives. The railway is complete, tested, and certified. Ceremonies are held to mark the opening and beginning of revenue service. Officials are invited. The public is invited. Media covers the opening. It is a significant day in the community's history. The opening ceremony typically includes speeches and official activities. Dignitaries cut ribbons. Plaques are unveiled. Speeches celebrate the achievement and discuss the railway's expected benefits. Local officials, railway executives, government representatives all speak. The first revenue train is prepared. Passengers are selected. Sometimes dignitaries, sometimes lottery winners from the public. The passengers board the train, taking their seats. The train crew, the driver, guards, and service crew, prepare for the first revenue journey. The signal clears. The train driver releases the brakes and advances the throttle. The diesel engines, or electrical system if the train is powered electrically, come to life. The train smoothly accelerates. The wheels grip the rails and the train begins to move. Watch the train depart. It moves slowly at first as it leaves the station, then gradually increases speed as it enters the open track. The acceleration is smooth and powerful. The train gathers speed, 20 kilometers per hour, 30 kilometers per hour, 40 kilometers per hour, accelerating as the driver continues to open the throttle. The train proceeds along the railway that took months and enormous effort to construct. The track is smooth. The train travels with minimal vibration. The rails are perfectly aligned. The train follows the design path exactly. The overhead system delivers power reliably. The electrical systems hum with energy. The train navigates curves smoothly. The superelevation banks the curves slightly, the centrifugal force balanced with the track geometry. Passengers feel their weight shift slightly as the train banks into the curve, but the motion is smooth and controlled. The train approaches the tunnel. The entrance portal grows closer. The train enters the darkness, having passed through the mountain so carefully excavated by tunnel boring machines. The tunnel is lit by the train's headlights and by the interior lighting of the train. The walls of the tunnel pass beside the train, showing the work of the tunneling effort. The train emerges from the tunnel into open air on the far side of the mountain. The tunnel has been successfully conquered, and the train carries passengers through it, demonstrating the triumph of engineering over geographic obstacles. The train continues and approaches the bridge. The structure becomes visible as the train approaches. The bridge stands majestically, spanning the valley that would once have prevented the railway from reaching this area. The train accelerates as it enters the bridge. The steel and concrete structure carries the weight of the moving train effortlessly. Looking out the train windows, passengers see the valley passing far below. The engineering marvel carries them across a gap that would be impassable on foot. The journey across the bridge takes only minutes, yet it represents months of construction effort and engineering achievement. The train descends from the bridge and continues to the next station. The platform is prepared, workers stand ready, and as the train approaches, the driver begins to brake. The train smoothly decelerates, speed dropping gradually. The train arrives at the station precisely on schedule. The train stops alongside the platform, aligned perfectly with the station design. Doors open and passengers alight onto the platform, completing the first revenue journey on the new railway. They depart the station, carrying memories of the first journey and marking themselves as pioneers of the new service. The train crew makes announcements and operates the train according to standard procedures. The extraordinary becomes ordinary. The new railway, celebrated in opening ceremonies, settles into daily operation. Trains will depart this station dozens of times daily, carrying thousands of passengers weekly. The railway becomes part of the community's transportation system. A railway is far more than steel and concrete, more than machinery and electrical systems. It is the culmination of human vision, remarkable engineering knowledge, and absolutely persistent effort through adversity and challenge. Thousands of workers contributed to this railway. Surveyors spent weeks in the field, measuring and mapping. Excavator operators moved millions of tons of earth. Tunneling crews worked underground in harsh conditions for months. Bridge builders created elegant structures spanning impossible distances. Rail layers ensured precision that would last decades. Equipment operators, electricians, welders, concrete workers, safety inspectors, engineers, managers, and countless others each played a vital role. Each person was necessary. Each contributed their expertise and effort. The railway is truly a collective human achievement. The engineering required to construct a railway involves remarkable knowledge and sophisticated technology. Materials must be selected for their properties. Steel chosen for strength, concrete for permanence, ballast selected for particle size consistency. Stresses must be calculated. How much weight will the bridge carry? How much deformation is acceptable in the tracks? Tolerances must be set. Rail gauge precise to millimeters, signal positioning to centimeters. Every component must function reliably. The signaling system must never fail to protect trains. The electrical system must deliver power consistently. The track must remain aligned through temperature changes and train vibration. The tunnel must never collapse. The bridge must never fail. Failures are not acceptable. They endanger lives and disrupt service. The railway will serve for decades, perhaps a century or more. The infrastructure investment will be repaid many times over through the service it provides. Millions of passengers will travel on this railway. Billions of tons of freight will be carried. The economic benefit will extend far beyond the railway itself, connecting communities and enabling commerce. But for most users, the railway is invisible. Passengers board a train, travel to their destination, and perhaps never contemplate the effort and engineering that enables their journey. Freight customers ship goods via rail without consideration for the infrastructure. The railway operates silently in the background, taken for granted, performing its service day after day. Yet this railway represents one of humanity's greatest achievements. The transformation from empty landscape to functioning transportation network is not trivial. It required vision, knowledge, resources, and persistent effort over months or years. It required thousands of people working in coordination toward a common goal. The railway connecting communities, enabling commerce, facilitating travel. This is infrastructure. This is the foundation upon which modern civilization is built. Roads, railways, airports, ports, electrical systems, water systems, communications networks, all of these represent the collective achievement of humanity to create the systems that enable modern life. As you travel on this railway in the future, taking it for granted as you travel from station to station, remember the effort that went into creating it. Think of the surveyors measuring the route, the excavators clearing the land, the tunneling crews boring through mountains, the bridge builders spanning valleys, the rail layers ensuring precision. Think of the electrical engineers designing the power system, the signaling specialists creating safety systems, the construction managers coordinating thousands of workers. The railway is not just steel and concrete. It is human achievement. It is the application of knowledge, skill, determination, and cooperation to accomplish something remarkable. It is infrastructure that will serve society for generations to come. Thank you for joining us on this journey through railway construction. We hope you have gained appreciation for the complexity, precision, and effort required to build the transportation networks that connect our world.
low frequencies, breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Exit shift like clouds in the dark. A symphony of cogs finding their spark. Atmosphere fades like a fading dream. The hum recedes into the machine. Warmth dissolves into the still serene. A gentle hum from the heart of the machine. Warm currents pulse through circuits unseen. Low frequencies breathing slow and deep. Metal whispers in the quiet glow. Sparks of rhythm softly start to flow. Tessers shift like clouds in the dark. A symphony of cogs finding their spark. Me fades like a fading dream. The hum recedes into the machine. Warmth dissolves